Welcome. Today is Wednesday, October 24th, 2018, and this is the NERI SimCenter's Advances in Computational Modeling and Simulation seminar. For more information, visit the NERI website at designsafe-ci.org, where you can find links to the SimCenter's Learning Center. Today's webinar is coordinated by the Natural Hazards Engineering Research Infrastructure's Computational Modeling and Simulation Center. This webinar is supported by the National Science Foundation under awards 1612843 and 1520817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. Today we're joined by Alex Taflonidis. He is Associate Professor and Frank Freeman Collegiate Chair in Structural Engineering in the Department of Civil and Environmental Engineering at Notre Dame. He holds a concurrent position at the Department of Aerospace and Mechanical Engineering and is also a faculty fellow at the Kellogg Institute for International Studies. His research focuses on uncertainty quantification and uncertainty conscious analysis design, with main applications on natural hazard risk mitigation and sustainability or resilience of civil infrastructure systems. The title of his presentation is Uncertainty Quantification, Computational Advances for Natural Hazard Risk Assessment. And Professor Taflonidis, I invite you to begin.
Thanks, Matt. Thank you all for joining us. I'm going to start with an overview of the webinar. So in this webinar, I would like to visit or revisit natural hazard risk assessment from a broader UQ perspective. Our goal here is going to be to discuss the efficient estimation of risk for natural hazards in a framework that puts no constraints on the adopted numerical and probability models. And since we'll talk about UQ, let's try and clarify what we mean by that. UQ is broadly defined as the science of characterizing, propagating, and managing uncertainty in real-world systems. It addresses the problems associated with incorporating the complete knowledge that we might have about the real world or the actual variability of the real world into an engineering system predictive analysis. In general, it has experienced tremendous advances the past decade, primarily due to rapid developments in computational science and computational statistics. And now, the different tasks that one can define within UQ can be categorized as uncertainty characterizations, in other words, defining the uncertainties that impact our predictions, the propagation of uncertainties, so propagating these uncertainties from the characteristics of the model to actually the statistics and the output of the model, sensitivity analysis, figuring out what type of uncertainties are important, Bayesian, updating, coming and using data, inferring things about our models or about the predictions related to that models, and ultimately optimization, broadly speaking, design under uncertainty. So in generally, like in the SimCenter, we try to address these tasks from the perspective of computational, simulation and the existence of multiple module tools that require interoperability of approaches. Pretty much UQ is an integral part of a lot of the tools point out here that the SimCenter is developing. And this is our long-term, aspiration, and ultimately our objective related to UQ and the SimCenter is to not develop new UQ algorithms, but integrate state-of-the-art UQ tools within the SimCenter workflow that help users address the various sources of uncertainty in their application, especially users that might have limited prior exposure to UQ, and also at the same time provide UQ experts with test beds in which they can deploy and test their algorithms in a real application setting. Broader overview of our aspirations. In this webinar, I will broadly talk about some of the UQ tools, focusing especially in the first 3 tasks. I'm not going to touch Bayesian updating or optimization at all. this is the outline of the talk. Unfortunately, we had a healthy scratch from our lineup. I don't think I'm going to have time to talk about multi-fidelity surrogate modeling, and because actually the example that I would bring, some aspects of computational wind engineering inside the talk. Unfortunately, we won't have time for that. So let's have the first topics, and the question I would like to address here is how to pose the natural hazard risk quantification problem in order to easier integrate advances for the broader UQ community. So let's start with the current standard of how we quantify risk, and generally we do this in the context of performance-based engineering. So the example that I have here is from performance-based earthquake engineering, but the workflow for other hazards, it has all the same essential elements. Now, from a traditional risk quantification perspective, we can distinguish the modules within performance-based engineering to an exposure, a vulnerability, and then consequences. Broadly speaking, excitation, response, and performance. I'm going to carry this distinction, but I'm going to try to simplify a little bit the characterization. So ultimately, risk in PBE is ultimately expressed through the integral that involves the conditional distribution associated with this module. An equivalent way to describe the risk is to consider directly the uncertainties that impact and create these conditional distributions. So these are my three modules: excitation, structural model, and performance. Like the first two provide my response. Generally, we call this the engineering demand parameters, the EGPs. And ultimately, the performance measure quantifies the performance, or the losses due to the exposure to the natural hazard associated with those EDPs. The underlying assumption in this presentation is that obtaining the EDPs is computational time intensive, but then evaluating the losses given those EDPs, it doesn't entail a significant computational burden. Of course, there are a lot of uncertainties that impact these individual modules. For example, if we're looking at earthquake engineering, based on the distribution of the regional faults, we're going to have a probability distribution function on the moment magnitude and rupture distance of seismic events. And similarly for the structural model, depending on the model that we're going to assume, we're going to have some uncertainty in the model parameters. For example, if we have a lumped a plasticity model, we might have uncertainty in the characteristics of the moment curvature relationship of the plastic hinges, as shown here at the bottom of the slide. So a lot of uncertainties that impact that influence the three different models. Assigning a probability distribution for these uncertainties ultimately allows us to quantify risk. It's simply going to be the expected value of our losses, which is a function of our EDPs over the domain of uncertain model parameters. Like through a proper definition of weights, you can encompass in this simplified characterization every flavor of risk that you are interested in. Like the benefits of this risk quantification, what really makes it appealing for integrating UQ algorithms is that we can explicitly write our risk integral with respect to the sources in the model parameters that come and create that generate this risk. Ultimately, what we denote here as theta. And for the most UQ approaches, you need to explicitly, mathematically at least, come and see this dependence. Now, to generalize approach, I'm going to even more broadly talk about input computational model performance evaluation. Modules. In other words, we don't necessarily need to have a structure involved somewhere in the workflow. Now, the first two modules give me the output, and I'm going to make a further distinction here at the red line. Everything after the red line, I'm going to assume that it from the computational perspective, it's easier to calculate. This doesn't mean that the performance evaluation module is not important, simply that from the computational perspective, I'm really worried about how I'm going to calculate the statistics of the EDPs. After that, everything is relatively computationally simple. Now, if your performance evaluation model has, it's also computationally challenging, then you can simply come and migrate it and incorporate it into the computational model. So ultimately, at the context of this presentation, we're gonna, be stopping at calculation of risk directly with respect to the EDPs. I'm not gonna go down the road into quantifying this performance and to really calculate, losses. And now, with respect to the uncertainty, I'm gonna further make a distinction between uncertain model parameters and stochastic high-dimensional input. To better understand this distinction, let's take an example. Go back into earthquake engineering. Let's assume that we try to describe our hazards through a stochastic ground motion model. What that ground motion model does, it comes and modulates a wide sequences through different, functions that address, temporal and frequency characteristics of the excitation to end with a final, ground motion. Now, this, the specific model that I'm actually going to use later in the presentation is the one developed by Rezaian and the Curagian. It has, some model parameters, some features of this, frequency and temporal characteristic of my ground motion, but also these, model parameters are related through predictive relationship to seismological parameters, mainly the moment magnitude and the rupture distance. So ultimately, the vector of model parameters are these, 6 guys on top of here, and also the moment magnitude and rupture distance. And my stochastic input is really this white noise, sequence. A feature of this stochastic input that, first of all, it's very high dimensional. It depends in this case on this discretization that you're going to do in time, and also that even though the whole white noise as a whole sequence can have a significant impact into the overall risk, individual components of this, sequence, in other words, what is the white noise at time 5 and in time 5.01, those individual components on their own don't have a big influence. Only the white noise as a whole sequence will impact risk, not the individual components. And similar, you can have in the computational model, you can have some, set the model parameters and some, stochastic high-dimensional input. This can be a discretization of a random field, a discretization of a stochastic sequence, as we just saw. Augmenting this, type of models, ultimately you end up with your computational unit, sort of your numerical, a simulation that's going to come and provide the response, the EDP, the output, with knowledge of this in general low-dimensional vector theta and the high-dimensional stochastic input W. Now, assigning a distribution to these model parameters ultimately, as we saw, comes and allow us to quantify risk. And in general, the different type of statistics that we might be interested in this risk quantification could be, for example, the distribution of your output Z. Again, you can come and propagate the uncertainties from theta and W to Z, and you end up with using the top probability theorem with an integral something like this. You might be interested in the statistics, but depending on what flavor of statistics, mean, variance, correlation, you have a different definition of this function f of k. And then if you're interested, in the probability that the NDP is going to exceed some threshold, this pretty much is very useful in natural hazard loss assessment because it relates to the fragility of individual components. Again, using the probability theorem, it can be expressed in a form like this. So ultimately, we have a risk that's going to be the expected value of some function h, and depending on what really the statistics I'm interested, I have a different flavor of what this h is going to be corresponding to. Always it's expressed with respect to my EDPs, and I'll have this high dimensional integral with respect to the uncertainty in the model parameters and the stochastic input W. As a note, you're going to see that in a lot of the in the presentation here, Ryan, I'm going to assume independence between theta and W. This is actually not necessary. Everything I'm going to present can be similarly derived if there is no independence. Simply, whenever you see in my notations P of W, come and replace it with the P of W given theta. In other words, in this case, there is a dependence between my stochastic input and my model parameters theta. Now, in summary, this is the problem that we are interested in. We have a system that, it can be any system exposed to some hazard that provides our output of interest Z. Now the system has, as input a high-dimensional stochastic input W and a lower-dimensional, vector theta. Now, assigning probability distributions to theta and W, ultimately I can come and quantify risk as the expected value of some function H. I would like to point out here that I'm not going to focus that much on what is the definition of these uncertainties. I'm going to focus on how we propagate these uncertainties, to calculate the system level risk. Also, we're going to further assume that obtaining the output may correspond to a black box numerical model. So in other words, we're going to come and focus on how we can really estimate this risk without having to call many times our expensive numerical code. This is the setting of how we're going to quantify risk to make easier to grab advances from UQ and directly apply it. Now let's move into the next part of the talk, which is going to be simulation-based risk estimation. So ultimately, how we're going to calculate this risk integral. Now, traditionally, some of the easier approaches is to use point estimation methods, something like form or first order, second moment. Generally, approaches that rely on some expansion of the integrand around a single point. Generally, they can be very efficient, but generally they're very approximate, and generally they need to be also repeated for each different risk characterization, for each different definition of H. Now, on the other hand, you have stochastic simulation methods. In this case, you can explicitly, as we're going to see, you can control accuracy, but these methods might require significant computational effort. Of course, the good news is that advances in computational science and computational statistics are drastically decreasing the barriers associated with the stochastic simulation methods. And since they have the potential to offer high accuracy estimates of our risk, this is going to be the main emphasis of our work within the SimCenter. And for those of you that have not seen how stochastic simulation works, you start by simulating some samples from your uncertain model parameters, theta and W's, and then for each of the samples, you go with the computational model and evaluate your performance function H. You repeat this for each of your samples independently, and after you have all the evaluated for all your samples, you go and approximate a risk as the sample average. You note here that for the thetas, I didn't necessarily come and use as my density for my samples a Q of theta, P of theta, the initial distribution, but I came and introduce a proposal density Q of theta. It's going to become evident in a few slides why I did that. If this directly corresponds to P of theta, this corresponds to Monte Carlo simulation, like crude Monte Carlo simulations, but in general, you can use some other proposal density. Now, apart from an estimate of the risk, we also can calculate how accurate is that estimate. So in other words, we can come and calculate the coefficient of variation delta of our estimator. Now, also, this approach is going to come and simultaneously provide estimates of the risk for any quantification that you want. So, in other words, you don't need to come and repeat it for each different h of k that you're interested in. But more importantly, it puts absolutely no constraints on the adopted numerical and probability models. And every type of a model that you want to incorporate with this setting, you can. Now, the bad news, of course, is that you require n calculations of your potential computational expensive model in order to calculate the risk once. And of course, this n comes and impacts the accuracy of your estimate, and the relationship is like this inverse proportional relationship to 1 over square root of n. So ideally, we would like to be able to calculate risk without requiring that many calls. Like, we're going to try to keep n moderately small, and we're going to see how we can accomplish that. Of course, with high performance computing, you can leverage high performance computing to simplify, to accelerate computations. This is what we call embarrassingly easy to parallelize problem, because pretty much each of your model evaluations, since they're independent model evaluations, if you have multiple cores, you can come and exploit all the cores to in parallel perform your computation. So let's go back and try to demonstrate some of these ideas in illustrative examples. So I'm going to use here, a seismic risk example, a 3-story structure, with uncertainty involved in a lot of components of my hysteretic model. And for the excitation, I'm going to use the model that I talked about earlier, the stochastic ground motion model by Rezaian and Regan, with some advances that we recently were able to establish that allows to modify this model to match any desired ground motion predictive equation that you want. My structural model has 15 parameters. My excitation model has 2 seismological and 6 parameters of the ground motion model, so in total 8 parameters. And actually, in some of the results, I'm going to consider a simpler variation of this problem, and I'm going to treat these guys deterministic. So in other words, I'm going to have in the excitation, I'm going to only have uncertainty in the moment magnitude and the rupture distance in the seismological parameter. In the case 2, actually, the predictive relationship that I'm going to use for the ground motion model parameters, I'm going to have additional uncertainty. Quickly, some results. This is the probability that the drift ratio is going to exceed some threshold beta. This is information that we really need in order to define component fragility within the concept of seismic loss estimation. And this is for the first story results, and this is for the third story. This is why I was talking before, that you can come and calculate multiple risk quantities within a single stochastic simulation and run, compared to the point estimate methods that you need to repeat for each risk characterization that you want. So in this case, we're able to get the entire curve, and in each point in this curve is a different flavor of risk, but also we're able to get the curve for different EDPs, in this case, in different stories of the structure. And we were able to get this curve with one stochastic simulation. These are results for the case where I do have uncertainty that I don't have uncertainty in the ground motion model characteristic, what I talk about case 1, and this is the result for case 2. Now, let's pose a different question. Let's say that I wanted to update the risk. Let's say let's happens if we come and change a little bit the probability model. So I'll go from P of theta, P theta prime. How do the results change? Do I have to repeat the whole process again? Through the introduction of this proposal density for theta, actually I don't have to, because if we come and recall on where we had to act, the samples from which I had to go and run my simulations, there were samples of this proposal density Q of theta that's not related to P of theta. So I can come and use exactly the same samples. So in other words, I don't have to repeat any of the computational expensive simulations and get immediately an estimate for my risk for this updated now probability distribution for my model parameters. So going back in our previous example, I modified a little bit the characteristics of my probability distributions, and now I can come and get this updated risk curve. And the key point here is that I was able to come and obtain these updated curves for exactly the same computational burden as I had before. I didn't come and repeat no simulations. I can even come and do this for multiple updates of my probability density functions. Here you can see 3D plot of changing the mean of the rupture distance or changing the characteristics of the truncated exponential distribution for the moment magnitude, and now get very easily this updated curve of what is the probability that the drift in the third story is going to exceed a drift of 1%. The key point here is not necessarily like the curve. This is going to be really dependent on the problem. I'm trying to stress the fact that we're able to get this curve for exactly the same computational burden that I would need in order to estimate the risk only for one point. And this is one of the benefits that we can get when we rely on stochastic simulation for calculation of risk. So this is sort of, in this case, we're able to get a parametric sensitivity of how the characteristics of the probability distributions impact risk. More broadly, we can talk about global sensitivity analysis, for estimating, a risk. And the simplest way to do this is rely on evaluation of Sobol indices, which pretty much, are for any subset of our model parameter. It can be an individual, model parameter, for example, just coming and looking the importance of the moment magnitude before, or for groups of parameters. Let's say that we want to come and group all the stochastic ground motion parameters together. So the Sobol indices are pretty much the portion of the total variability that's attributed to these components theta c. So the numerator is simply the variance of the conditional expectation of h with respect to theta c. Sort of you have here two different probabilistic integrals. The inside integral is with respect to the remaining parameters excluding theta c. This is what this notation means. And then the outside, probabilistic quantification is the variance with respect to the theta c. So this Sobol index pretty much corresponds to the portion of the total variance that is attributed to theta c. It's a measure of the global importance of theta c compared to all the remaining components. And these are what we call the first order indices. In general, you can talk about higher order interaction indices. In this case, they come and give you what is the interaction, what portion of the total variability can be attributed to the interaction between two model parameters. You can see that in order to calculate this, you calculate the total variance for theta c and theta m, and then just to isolate the interaction, you go and you subtract the individual indices for theta c or theta m. Now, these are very powerful indices. The challenge is that calculating them is not that easy, because you can see here that in the numerator you have sort of a double loop, in integration, the conditional expectation, and then the variance of the conditional expectation, and you have to come and repeat this for each different component that you are interested in. Of course, there are the main approach of calculating these Sobol indices. You can do it with Monte Carlo, quasi-Monte Carlo approaches. You can actually do it with emulator approaches, and then you can do it with approaches that try to approximate the marginal distributions, either the PDF or the CDF of the response. The results that I'm going to show next, I leverage one of these approaches that rely on approximating marginal distributions. So these are results for case one for the risk quantification that just corresponds to the mean drift ratio. You can come here and have grouped actually a lot of the parameters that are related to the stiffness or the yield strength or the post yield of my structural model or the damping of the structural model. You can see here that the Sobol indices are exceptionally small. This is an indication that these parameters are generally unimportant, that even I can come and completely neglect the uncertainty in their characterization, and I'm going to end up with the same risk quantification. And the two important ones are definitely the moment magnitude and the rupture distance. But you can sort of change the flavor that you're interested. You can come and, let's say, rather looking at the mid-drift ratio, looking at the probability that the drift ratio is going to exceed some threshold, you can come and do it for different stories, and sort of the results might change. But you can see here the underlying trends. That generally the structural model parameters are important, the two seismological parameters are very important. But of course, you can come and do this for interaction between the two seismological parameters as well, and especially when you move towards the sort of the more rare events, moving from mean drift, the probability that the drift is going to exceed some threshold, you can see that also the interaction between MR9 rupture starts becoming important. You can repeat this now for the case 2, where you actually do include uncertainty predictive relationships. You can see that all of a sudden the importance of the moment magnitude and the rupture distance decreases, and the importance of the ground motion parameters increases. This is attributed to the fact that one of those ground motion parameters that included there is the area's intensity, that comes and directly scales the intensity of the excitation. And again, the results are not, the specific results are not important, because they're going to really come and depend on the specific case that you're going to be interested. The critical insight that I want to gain from this is that you can come and use this global sensitivity analysis indices to very in a very straightforward manner come and provide you insight about which of the uncertainties in the problem are really influential. In the previous case, I can come and say, look, I can neglect completely setting the structural model parameters, and I'm still going to end up with the same result. Moment magnitude rupture distance is important. When I moved into the case where I do have uncertainty in the ground motion model parameters, I realized that that uncertainty tends to dominate the risk, even though there is importance from the moment magnitude and rupture distance. And definitely there seems to be importance, both the correlation between the seismological parameters and the ground motion model parameters. This is if you come and from the sort of the index for all the excitation parameters, you come and reduce the individual component, you're going to see that interaction level, at least when I'm talking about probability of the drift ratio exceeding some threshold, is going to be pretty significant. Final discussion about the stochastic simulation before we moved into surrogate models, variance reduction. So, I'm going to come back and revisit this selection of Q of theta. You can generally manipulate this Q of theta and probably select to try and reduce this coefficient of variation. This is the idea behind importance sampling, where you try to move your computational effort from in concentrating in domains where the integrand of this risk integral is important. So this is the idea behind importance sampling. Generally, the optimal importance sampling is the density that's directly proportional to the integral, and for theta, we can just come and use the marginal distribution of this, a joint distribution for theta and W. Of course, most of the times it's completely practical to come and use this density because you really don't know it. So the question is how we can select this, distribution. So we can choose a family of distribution parameterized with some parameters, as for example, a mean with some specific mean and Gaussian with a specific mean and variance, and then we try to select this S to minimize the coefficient of variation. In other words, to minimize the square root of the variance that appears here at the numerator. Now, if we have performed some analysis, perhaps with a different proposal density, we can use that information to calculate what this projected variance is with a new importance sampling, and then try to select the optimal values of these parameters. This is, first, there you can have challenges in high dimensions or in random variance. That there do exist, or approaches that you can address these challenges. Let's now demonstrate this in our previous example. Let's assume that we wanted to have a coefficient of variation less than 2% for a probability of my RDP exceeding some threshold, and we start very naively thinking that we'll have a high performance cluster, so we're going to rely on doing a lot of simulations. After we get the first 1,000 simulations, and we get an estimation. In this case, I started with doing crude Monte Carlo analysis, and so we have some estimating of the risk and some approximation of the accuracy, the coefficient of variations, and through the proportionality here with square root of n, we realize that we need 10 to the 5 runs to achieve the desired accuracy. We could have naively continued in the same path, but at this point we stop. We formulate the problem that we saw in the previous slide. Then we propose an important sampling density. In this case, I did it only for the 2 influential parameters, and understanding from my results of the global sensitivity analysis that the remaining ones are not important. So I'm concentrating on these 2 to better leverage the limited information I have, and then I formulate a new important sampling density, and then I go and update the risk. And in this case, we managed to achieve this, coefficient of variation of 2% using simply 2,500 additional simulations. So significant, computational benefits by smartly coming and leveraging my initial computations to improve the important sampling densities. And why this important sampling density in this case gave us, I think it was a 30-fold reduction of the computational effort. This is the initial density. This is the densities that we ended up using, and we were comparing them to the actual optimal density. Actually, this is an optimization, an approximation of the optimal important sampling density using kernels. You can see that the one that we actually use and the optimal ones are fairly similar, but these 2 distributions, the initial probability distribution and the important sampling distribution, are really significant and significantly different, and this is what gave me the 30-fold improvement in the computational effort. As expected, the important sampling densities concentrate in regions for the moment magnitude and rupture distance that corresponds to stronger events. Okay. Wrapping up the stochastic simulation, now let's come back and talk a little bit about surrogate model. The overall goal that we have in UQs is address the model complexity of our simulations. So this can be done, as we already discussed, accelerating computations, doing parallel and distributed computing, or coming and using some advanced stochastic simulation techniques. The other approach is to come and reduce a little bit the complexity of our models. So we can come and use reduced order modeling, or multi-fidelity modeling, where you come to combine informations from models with different fidelity to end up with an efficient and accurate estimation of risk. In this case, you do have to come and combine it with some smart algorithms that can efficiently combine the information for your different models. The fifth option, what I'm going to concentrate for the remaining of the talk, is coming and using surrogate modeling. So surrogate modeling probably is going to become, evident, so that we can sort of come and integrate it with multi-fidelity or advanced simulation techniques at the same time. For those of you not familiar with surrogate models, they're data-driven mathematical approximations of the input-output relationship of a complex numerical model. I'm going to denote input X and the output Y. I'm going to come and discuss, later what these 2 should be in the context of the risk assessment problem that we're interested in. How the Metamodels developed. So the formula is based on a database of simulations of the initial computationally expensive model, what we call training or support points, or actually very frequent experiments. I should caution you here that this is computer experiments, simulation experiments, not necessarily physical experiments, but that is the terminology that's established in the field. And with this information, now we can come and develop the surrogate model approximation. There is a variety of different metamodels. Especially for UK applications, we tend to like a lot Gaussian processes. It's going to become evident in a few slides why. So in Gaussian processes, the real function is approximated as a stochastic process, as a Gaussian process that also involves a global regression, a component approximate through these basis functions beta. So ultimately, your real response is a Gaussian with some predictive mean and predictive variance, and you can go and calculate what the predictive mean and the predictive variance is. Then details are not really important. What I want to stress here is that you can see like both the predictive mean and the predictive variance are, very simple mathematical expressions, very simple, a matrix manipulation that involves no new matrix inversions compared to the matrix inversions that we needed in order to train the Metamodel. So after we have the Metamodel coming and making forward predictions, it's expensively computationally efficient. It's very inexpensive. We can do thousands of simulations in just a few seconds. Like graphical representations of how this process works. I'm going to use a one-dimensional, example. This is the exact function. We have evaluations at some experiments, and then using this information, we're going to tune the Metamodel. In this case, it corresponds to the optimization of the hyperparameter of the correlation function of our Gaussian process. You can do this with different approaches. Most typically it's done with maximal likelihood estimation, but you can, use something like a cross-validation. So after you have the tuned Metamodel, now you can come and calculate what the predictive variance is, but also you can, what the predictive mean is, the blue line, but also you can come and get what the predictive variance. Sort of this is a quantification of the variability of the Metamodel predictions. You can see the predictive variance is exactly 0 at the training points. Gaussian processes are interpolators, so at this point the errors is 0. So for making forward predictions, you can potentially simply use the predictive mean, or you can come and incorporate the predictive variance. In other words, here I'm plotting the plus or minus standard, a deviation with respect to predictive mean. So rather than entirely relying on the blue curve, you can come and get realizations of the Gaussian process from the probabilistic nature of your Metamodel. And the critical thing about any Metamodel, it is the tuning. That's also important. But the even more critical thing is the design of experiments. So sort of you can see here a comparison of a Metamodel with 5 experiments, and then when I add additionally 3 experiments, you can see that the predictive variance significantly reduces here at the bottom, but also how the predictive mean comes and matches the actual function much better. So this design of experiments is very critical. You can naively do something like space filling, or you can use an adaptive design of experiments. Now in that case, you use the Metamodel that you already have with a limited number of experiments, and especially the fact that the Metamodel also gives you the predictive variance, not just the predictive mean, so that it quantifies the variability of the predictions. You can use the information to come and figure out where should the new experiments be. So this presupposed as an optimization problem of selecting the new experiment to sort of maximize some design of experiment DOE criterion. So this is it's an open problem, like design of experiments. It's still, and it's an open problem from the UQ community. Generally, it involves a challenging optimization, and also it's well known that this problem for most type of applications and design of experiments criteria, it has multiple local optima that give you a similar, DOE criterion values. Now, rather than trying to solve this complex optimization, an alternative approach is to do what we call sample-based design of experiments, where you try to approximate the the previous problem, but in a computationally much more efficient way. So a few slides to demonstrate that. Like, this is the information that we have, and since we have also the variability, we can come and define a utility metric that pretty much comes and relates how the uncertainty in the Metamodel predictions really come and ultimately impact, a risk, sort of we're propagating this variability from Y into our risk. On top of that, we have to remember that we are using the Metamodel for a specific UQ task. So we can define a preference function that is related to the UQ task. One brief example, let's say that you are interested in using the Metamodel to estimate a risk, then sort of this preference function, in this case, would have been your integrand. of your risk integral. And in this case, it comes and tells you like coming and adding or improving the metamodel accuracy in domains like this is not really beneficial because the contribution to the integrand is very small. So with this utility metric that sort of is related to the metamodel accuracy and this preference function that is related sort of to the UQ task that you're interested in using the metamodel for, you can come and establish this sample-based design of experiments. So we start by simulating a large number of experiments candidate experiments, based on this preference function, then coming and using our utility and metric and the predictive variability of the metamodel. We come and reduce these experiments. In other words, we come and remove the experiments in the domains where the predicted variability of the metamodel is small, where we know that in these domains we're coming and doing a good job. And then we come and cluster this, a larger number of candidate experiments to the specific number of experiments that we're interested in. This clustering we do because, all these, for example, all these candidate experiments, because in the same domain, they ended up giving us information in the same domain in the input, so one will end up helping one another. So there's no point of including, simultaneously in all of them. So this ultimately gives us the DOE of adaptively selected experiments in domains where we're going to expect, to be important for our UQ task. We expect to get good utility because the initial information that we have in the variability in those domains is high, so the variability of the metamodel prediction is high, and at the end they're not close to one another. So why we like using Gaussian processes for UQ, as we already discussed, the computational very efficient, so you can do thousands of simulations in just a few seconds. They have been proven very accurate even for approximately complex functions. Also, if you want gradient information, you can very easily come and get it. And also the most important feature is they have this probabilistic, fully statistical emulator nature. The fact that it gives you an estimate of the predictive variance that also function of your hypnosis constant along the domain. Something that you can very easily use for adaptive DOE, or as I'm going to show in a few slides, to update your risk estimates. The challenge now is that the computational burden for training the metamodel, it's related to the number of experiments. You have the number of training points to the power of 3. So it's n to the power of 3. Or n is this number of experiments. This generally might limit the applicability in high-dimensional problems when you need a lot of training data to populate the entire domain. Of course, there are ways to address this challenge, but still, it can be significant for certain type of applications. Now, going back to our problem at hand, remember we tried to approximate. Let's say that we tried to approximate create a metamodel with respect to both all our uncertain inputs, so both theta and W, and because the high dimensionality of W, we have a challenge. Now, instead of doing that, we can consider the conditional on theta statistics and develop only a metamodel with respect to theta. Let's try to explain what do I mean by this. So let's come and consider the conditional distribution of Z given theta. So in this case, we propagate the uncertainty with respect to W, and we somehow, we can get this distribution. As soon as we have this distribution, we can express risk using this conditional statistic. For example, if we're looking at the probability that ADP is going to exceed some threshold, you can come and write these calculations with respect to theta, and also the conditional distribution of Z given theta. In this case, you don't see W at all in this risk quantification. Now, of course, the challenge is that we cannot really come and approximate this entire distribution with a metamodel. What we can do instead, we can fit some parameterized distribution for over the ADP. For example, we have the samples, we can come and fit a distribution from a family of distributions. For example, in Seismic, in earthquake engineering, this is frequently done with log normal distributions, but you can use something like a generalized extreme value distribution, and then you can come and approximate the parameters of that distribution, which broadly speaking, they're going to correspond to some conditional statistics for your EDPs. For example, if you're fitting a log normal, this is going to be the median and the dispersion of your EDP, conditional on the different theta values. Now, as soon as you have this fitted distribution, now you can come and approximate risk with respect to the fitted distribution. Where this approximation here comes from the fact that we're not using the exact distribution, but we're using this, fitted parameterized distribution. In this case, now we have the answer for what should be our input, what should be our output. The metamodel input is this lower dimensional vector theta, and the metamodel output, what we're approximating, is this conditional statistics that we need for the parameterized distribution. And in all reality, we don't have to do this with the entire theta vector. We can, just do it with respect to a subgroup theta c. In this case, what means that we are approximating the conditional statistics, a given theta c. So in other words, we're propagating here the uncertainty with respect to both W and also the remaining components of theta, so theta not c. Of course, how we're going to calculate this, we have to rely on Monte Carlo simulation, but because, in this case, this number of samples doesn't need to be that significant because the variability that we expect from W and theta naught C is not significant. So theta C's are important, group in terms of what creates the variability in the total risk. And with this, parameter, this distribution now we can come, with this approximation now we can come and calculate that risk, which is going to be a function now of H tilde, and H tilde is ultimately, it's approximating using the fitted parameterized distribution. So for example, going to our previous example, what the fitted distribution is going to look like, what H tilde is going to look like, so it corresponds to this component of the integral, which ultimately ends up being the complementary, CDF, and as soon as I have my parameters, this conditional statistics, I can very easily come and calculate what this fitted CDF is, so we have the approximation for H tilde. So summing up, this is how the metamodel-aided UQ analysis works. We have a training set, and based on that training set, training set our experiments, we evaluate through our model our response, or more broadly speaking, the conditional statistics if we don't, if we have a high dimensional problem, and then we use the tune metamodel to come and approximate risk, where in estimating this H tilde, we can either rely on only use the predictive means, so in other words, completely forget the fact that our meta model has a statistical nature, or come and exploit that statistical nature, and ultimately in this case we end up with an H tilde that's a function not only of the predictive mean but also of the predictive variance. Now, for many types of applications, you can explicitly come and get an analytical expression for this, H tilde as a function of the predictive mean, the predictive variance. But even if you cannot get an analytical expression because your meta model is so inexpensive to evaluate, you can come and sort of propagate the uncertainty using a Monte Carlo analysis. And as soon as you have this, now you can very easily come and calculate this risk through stochastic simulation. And the key here is that, because of how expensive the meta model is, you can come and use a large number or a large sample size. And ultimately, your computational cost comes from these model valuations, not from the large case N, but from the small case N. And ultimately, how accurate this risk is going to be related to how accurate your meta model is. I'm going to come back into this discussion a little bit later in the presentation. Let's come and demonstrate this into the previous Seismic example that we're looking at. This was the the hazard curve looking using the actual model. Now, in this case, we came and we developed a Metamodel only with respect to the moment magnitude and the rupture distance with respect to the two important parameters. Let's say if I only use the predictive mean, this is the curve that I'm getting. You can see that for lower, probabilities, I have some discrepancies. As soon as I come and incorporate like the Gaussian nature of my Metamodel, you can see that we have a little bit of a correction of those, hazard curves. And when we come now and add more experiments, I come and get a much better fit. I think the blue and the green curves, if I remember right, they were estimated using 200 experiments, and then I came and added, adaptively 100 more experiments to come and get this improvement. So this comparison here shows you that, exploiting, like the comparison between, red and green comes and tells you that exploiting the fully statistical nature of your emulator is important, and of course, when you get more experiments, you end up getting more accurate results. This other example, I think we're running out of time, so I'm going to go a little bit quickly. It's a hurricane risk example. In this case, we use a high fidelity, model. Actually, we use existing databases that we perform for regional, coastal, studies to come and train the Metamodel so we can predict the response for outputs that don't belong in the database. One of the challenges that we face here is we have a very high dimensional output, but you can come and use some dimensional reduction techniques, for example, principal component analysis, to address this challenge. I'm going to focus a little bit on the results. You can see here on the left the high fidelity model predictions, and for ATSIC, we actually think this is a comparison this is a combination of ATSIC and SWAN. This is the wave height around the Hawaiian Islands. We run around 2,000 CPU hours for each scenario, and our Metamodel predicts in less fraction of a second. And you can see that we have a very good match. And even if you come and do time-based predictions for the surge, you can see that the Metamodel and the actual high fidelity model, they have very good accuracy in the domains that accuracy a little bit lower, coming, looking like 1 plus or minus standard deviation of the predictive mean, you still have very good approximations. This is a result of coming in and looking, if I start and now increase the number of experiments, how does the accuracy of my Metamodel changes? This is the correlation coefficient, leave-one-out correlation coefficient of the Metamodel. This curve corresponds to the naive selection of the experiments, and the blue curve is if I intelligently come and use the existing experiments to inform the selection of the new experiments, either adding 10 at a time, or I think the circles are adding 8 experiments at a time, and then training a new model. You can see significant benefits, or of course, like how big the benefits are, it really depends on what you're going to use the Metamodel for. But even if you come and look with respect to risk estimation, you can still come and see that the advantages are significant. As we start increasing the number of storms informing the Metamodel, we come and very quickly converge to the real risk. Final part of the talk, I want to talk a little bit about the iterative Metamodel implementation. This comes and tries to address the challenge, what is accurate enough in terms of the Metamodel to perform accurately our risk estimation. Should I have a globally accurate, a Metamodel first, or I can perhaps leverage an iterative formulation to better guide me? So in the iterative formulation, we're going to start with an initial, training set. We're going to, tune our Metamodel, and then we're going to perform our UQ analysis. And then we're going to have some convergence criteria to ask ourselves how we converge or not. If the answer is no, then we're going to get new experiments, perhaps through an adaptive design of experiments, and then come and perform this task. now with the total number of experiments, go and tune the Metamodel, perform our Metamodel, aided UQ analysis, and figure out if our results have significantly changed in the new iteration. If they have changed, in other words, you haven't converged, we go and repeat this. And if pretty much between successive iterations we don't get significant different results, then we have convergence and we terminate the criteria. Ultimately, both the convergence criteria and the sort of the characteristics of the design of experiments are really going to be dependent on the specific applications, on really what is the UQ task that we are interested in. And an example of this for convergence criteria in a few slides in the specific applications that I'm going to be looking at. Now, after termination, the question is, what can we do? So we can either rely completely on the surrogate model, just be confident with the analysis that we have here, or we can go back and use simply the Metamodel, the surrogate model, to tune our UQ algorithms. In other words, to improve the algorithmic efficiency. Maybe this is like the selection of important sampling densities, but then come and perform the risk estimation itself using the exact numerical model, not relying on the Metamodel itself. This can help getting biased result for applications where we, for whatever reason, we end up having a erroneous Metamodel in part of our domain that does contribute to our risk. Specific example to come and demonstrate it. This is from the recent work where we simply developed the Metamodel actually within the iterative formulation that I talked before, simply to approximate the optimal importance sampling density. So this is not pi of theta, it's a pi of theta using a JPM, a Gaussian process Metamodel. But after convergence, we just used this as a proposal density. When we went and actually calculated the risk, we came and relied on the on the exact numerical model, not on the Metamodel. So the Metamodel was just used to come and very efficiently come and inform a proper importance sampling density. Two examples from this paper. One is the 10-dimensional truss example. The other is a fluorescence example that has 36 model parameters. They're definitely not low-dimensional problems. Risk here is quantified as the probability that either the acceleration of the server for the full acceleration example, or the displacement at either the middle of the span, at the middle of the truss, or the middle spans of the truss is going to exceed some acceptable threshold that we set. And we selected this threshold so that these probabilities correspond to a rare event, something that has probability of occurrence 10 to the minus 4 or 10 to the minus 5. Some results of this is our convergence criteria. So we came and at the end of each iteration, we came and approximated the PDFs, the optimal importance sampling PDFs that we're getting, and we used the Hellinger distance as a way to define this difference. And you can see that for all the examples that we looked at very quickly, we start with big discrepancies between the approximated PDFs, and then very quickly we reach a plateau and we drop below the threshold that was set from the beginning. Actually, we can even come and compare the discrepancy between the approximate importance sampling PDF and the actual importance sample PDF, and then we can, this is a correct result. We have here exactly the same behavior, but very quickly the discrepancy is initially big, and then very quickly we reach a plateau. Of course, the actual algorithm, only has information about the approximate PDF. So in other words, the convergence needs to be chosen based on this information. And this is as the sort of the iterations of the algorithms. What you have here on the x-axis, actually, the previous slides, is also what we had in the x-axis, like the number of iterations. Here you can see like the approximate failure probabilities using entirely the Gaussian process Metamodel. You can see that really the common converges to the actual result. Of course, what we're advocating is just coming and using the Metamodel to figure out what the importance sample, so the important sampling density should be, and at the end of the day come and use the actual model for the actual risk estimation. Here's some comparison results. We compare also with some of the other approaches. This smaller case n is the number of analysis that we needed in order to train our metamodel and convert to the important sampling density, and then total is the total number of simulations that we needed, because remember, we always have, we have a second state that comes and uses the exact numerical model now to come and do the risk estimation using the metamodel aided important sampling, densities. And even for the challenging for isolation example, 36-dimensional example, you can see that just with 2,400 simulations, we end up with very accurate estimate comparatively, for example, to the exact result from Monte Carlo, very accurate estimate of the failure probability for an event that's 10 to the minus 4. So compared to the Monte Carlo, significant computational benefits, but even compared to a very smart important sampling density that, in this case, it was only relying on using the exact numerical model. Again, significant computational benefits, and the benefits here come from the fact that, we used an intermediate, a meta model formulation to help us select the important sampling densities rather than relying entirely on the expensive model to come and guide that important sampling density selection. This is the conclusion of the talk, so I hope that I came and convinced you that stochastic simulation offers a versatile approach for UQ analysis, natural hazards engineering, and surrogate modeling can offer significant computational benefits for these UQ applications. Gaussian process meta models are especially relevant in this context due to the holistic treatment of the uncertainty, the fact that not only give you predictive mean but also give you predictive variance. You can exploit that to get better risk estimations, or simply to come and guide you the selection of experiments. Always, you should try to adaptively control the metamodel accuracy with ultimately goal to converge to accurate solutions, perhaps with inaccurate meta models in some domains of your model parameter space, as long as they're accurate in the domains that you are important for your UQ task. And generally, the iterative implementations facilitates a seamless way to accomplish this task. In general, you can entirely only rely on metamodel predictions, or you can come and use the metamodel simply to come and improve the algorithmic efficiency of your UQ algorithms, but then come and use the exact numerical model to perform in the end those UQ tasks. And finally, for risk assessment, for natural hazard risk assessment, we have to be carefully select what is really the input and the output of your meta model to come and avoid some unnecessary challenges that you might have with high dimensional inputs. I'm going to come back to this slide. Ultimately, addressing model complexity in UQ analysis is you can do it in multiple ways, and they all are important, and in all reality you should try to leverage all of them, and this is in the workflow that we try to establish within the SimCenter for UQ. This is what we're trying to do, and figuring out the proper ways to integrate these different algorithms to get efficient and robust, by robust I mean accurate, risk assessment results. If you have any questions, you can either address them questions either about this presentation or about the work for the SimCenter, within the SimCenter for UQ. You can either address them directly to me or in the Slack channel. I think Matt is going to give us information about the Slack channel next. With that, thank you very much for joining us, and thank you for your patience.
Thank you very much for the presentation. At this time, I know we're running late, but we have a little bit of time for question and answers if people are able to stay. The attendees are reminded to send questions through the chat function. You'll remain in listen-only mode, so send those questions to the moderator. I think I'm going to try to start with easy questions and work our way to more difficult ones. The first one is, how do you determine the number n needed for your Monte Carlo simulations?
Okay, so that's a very good question. The easy answer is you control the accuracy. Remember, like stochastic simulation gives you an estimate of your risk integral, but also gives you a coefficient of variation of that estimate. You can, at the same time establish both. So you should have, a target of what the coefficient variation should be, and through that you can, adaptively control and select what the number n is. Now the follow-up question is, what should your desired accuracy be? The answer to that, it really depends on what are you trying to do. Let's say that you are integrating, a Monte Carlo within a design under uncertainty problem, an optimization problem, and also you're going to come and leverage what we call common random numbers to reduce the relative impact of the stochastic simulation error. In that case, you can probably tolerate a bigger coefficient of variation, even something as big as 20%, and still, be confident that you're converging to the right optimal answer. If on the other hand, you want to only calculate risk, and you're going to calculate that risk accurately, a good number would be 2 to 3% of coefficient of variation. Okay.
Are surrogate models valid outside the data range used to train it?
Very good question. In general, as any interpolation technique, back from where we were doing regression, we all remember, try to avoid extrapolations. Having said that, mild extrapolations for Gaussian processes is, if you are careful with respect to the training, they will still work. But the trick there is mild. And the other trick is really how you have tuned your Gaussian process metamodel. Generally, the two main approaches for tuning are, maximum likelihood and leave one out cross validation. You should be very careful if you are going to use extrapolation with maximum likelihood. The accuracy outside of the domain drops significantly. If you have done something like leave one out cross validation, in general, you have a much, much better behavior for, extrapolation. Even though the first answer, everyone's going to come and tell you, yeah, try to avoid it. But in the cases where you do have to do it, be careful a little bit of your tuning. Even with respect to the tuning, you can come and give weights to the experiments that are sort of at the boundaries of the domain. So sort of you cannot do it, actually you can do it with maximum likelihood. You can much better do it if you're doing leave one out cross validation. You can give bigger importance on those points where you're calculating what is your leave one out, error, and that's going to help you a little bit start behaving better when you try to do extrapolations.
And a last question. In importance sampling, any thoughts on how the chosen importance measure can detrimentally after the sampling if not well chosen? So any thoughts on how the chosen important measure can alter the sampling?
Yeah, I mean, there is a lot of perhaps unfair, perhaps fair, criticism about the fact that important sampling can give you bias predictions. If you're not careful, so the challenge comes actually, let me come and go back into the exact slides. Yeah, you absolutely, you do have to be careful. And the challenge comes from the fact that your P over Q ratio has to be bounded. If that ratio is unbounded, you're going to come and get, a biased prediction. So in other words, this ratio here has to be bounded. Now, in the example that you see, I was very careful to select a proposal density that did not go to 0 faster than what the initial distribution goes to 0. This pretty much guarantees that this important sampling quotient is going to be bounded. A very simple way to do this is what we call defensive importance sampling, where rather than coming and using as important sampling density directly this Q, you use a weighted average between Q and P. That pretty much guarantees that your important sampling quotient, P over Q, is always going to be bounded. But absolutely valid question. You have to be careful. I always say that to some extent, important sampling does have some elements of art, but if you know the pitfalls to avoid, you can easily avoid them. Simplest way to do it is defensive, important sampling.
Okay, and one final last question.
We have time. I can stay if people have questions, Matt.
Okay, is the calibration process or training of the Metamodel computationally demanding?
Another very good question. It really depends on the number of training data that you have. So ultimately, from the computational perspective, the computational intensive part of coming and optimizing for like this alpha star and beta star at the end of the day, it is inversion of this correlation matrix. So this is, if you have 1,000 data points, this is going to be 1,000 by 1,000 data points. It's a sparse matrix, so you can take advantage of that and simplify it. But it's still if the number of training points that you have quickly increases, it starts becoming very computational intensive to come and do this inversion. The computational burden, if I remember right, is n to the power of 3, where n is the number of data points. So it can be, significant, but at the end of the day, the discussion comes, how expensive is your actual numerical model? For example, for the hurricane application that I was just talking about, a single analysis there requires around 2,000 CPU hours. So even training of my Metamodel, let's say it requires 5 minutes. That is very small compared to the computational burden for coming and calling my actual model to perform a simulations. But simple answer, if you are below 2,000-3,000 training points, the computational burden should not be significant. You should be able to train, and of course, depending on the approach that you have, MLE or leave one out cross-validation, within 3-4 minutes at most. If it starts exceeding let's say 10,000 points, you might need an hour. If it goes over that, we're at the point where you need to come and rely on something different, maybe hierarchical, Gaussian process in your domain. Maybe try to leverage even more sparse manipulations, tensorize your calculations to be able to train it. But I have seen results with these smart cases where people have been able to train Gaussian processes for 100,000 training points. Something that if you were to ask us probably 5, 6, 7 years ago, we might come and say, yeah, this is unthinkable.
Okay. Well, I think if there are any other questions, I suggest we take them to the NERI Slack channel, which is designsafe-ci.slack.com. And that brings us to the conclusion of today's Advances in Computational Modeling and Simulation seminar. On behalf of the attendees, thank you, Professor Tafilonidis, for taking the time to share this information with us. As a reminder, please check the SimCenter's website at simcenter.designsafe-ci.org. And check your email for announce@designsafe-ci emails that have registration links for upcoming webinars in the Early Career Researcher Forum, the Natural Hazards Engineering 101 webinar series, and additional Advances in Computational Modeling and Simulation seminar. If you haven't joined the Slack discussion, join us there. Again, it was designsafe-ci.slack.com. Register through the DesignSafe website, and thank you for attending today's forum.